All right, let's get started. Question right away. Can you speak up? It's dead.
It means like remotely, so you don't have to go on the website. You can actually do it from the landline.
I don't have a way to do it. I've heard that there is a way. I don't know how it works. So there's an API. There's a Python API that they publish, so you can use that to write a little Python program if you have the right credentials that you can do. So it should be doable, but yeah. Okay. So first of all, let's talk a little bit about the course and how things are going. I heard things didn't go so well in homework 3, and to be honest, I decided I would do the solution for homework 3 as well last night. And I think I found a bug in the template that could have tripped a few of you up. Sometimes there would be the heap kept moving around. Right? So the base address of the heap was shifting around, and the reason for that is, maybe we'll talk about this more later, but in Linux there's address space randomization just for security reasons, to make it harder to make an exploit. So they actually put the heap in different places. So that usually doesn't matter. To a regular program, you malloc, everything's fine. But now we were playing with malloc, and so that made things a little tricky if you weren't paying attention to that. So I can imagine that it didn't happen all the time, and certainly if you ran it in GDB, it never happens because there's no randomization in GDB. But I could see how that could cause some problems, so I'm sorry about that. So I will go through that solution a little bit today as well. But in general, homeworks in this class are of course intense. They're intense in all the classes that I teach. There's two reasons for that. Right? One is, Tim said yesterday that he felt bad for you guys because you're not good programmers. Right? So it's hard. But the whole idea is you're supposed to become good programmers here, and the only way to get good is to do a lot of programming. So we do real things. It's not a bunch of hand-holding or do this, do that. It's more like figure this out, and we'll try to help you along the way. Okay, so that means you're not always going to get the full score on the homework, because sometimes it's just too hard. But that's all right. Okay? We very seldom get a lot of people with a full course score in these classes. Sometimes it happens that one or two people get 100%, but it's very unusual. The median is usually about 50%, which means if you miss a couple of these homeworks, you shouldn't feel too bad about it. Right? Just get back on the horse and try harder next time. Right? Also, many of the homeworks don't actually require a lot of work. A lot of actual typing. So my solution for this was about 40 lines of code, in addition to the template, right? And so those 40 lines require some thought, and sometimes you can't just sit down the last day and just figure it out right then. Right? So the better approach is to get started in the lab, obviously. Right after the lab, like when you get home, try to figure out some more things until you run into a real problem, so you have something to think about for a while. You can post something on Piazza, you can come to my office hours on Wednesday, you can come to Tim's office hours on Thursday. There's lots of chances to get lots of help, but I didn't have anyone in office. I had one person in office hours last Wednesday. Tim, I think, didn't have anyone, so that's kind of a wasted chance there. Okay. Right, and then there's the exams. The exams are no easier than the homeworks. In fact, the best way to get a high course score is to work your butt off on the homeworks. Because the exams can be a little unpredictable, right? Did you really study for the right stuff? And maybe you're not used to this kind of questions, that sort of thing. So there's a lot of variance in the exams, depending on how you feel about things. But in the homework, if you got it right, if it works, right? You just have to put some more time into it. So you can sort of predict what's happening there. With the exams, it's a little harder. So I've had some people one guy got a C in class. He did great on the homeworks. He did absolutely rotten on the exams. So he got a C. He scraped by with a C, I think. I don't remember. But anyway, he came back the other day, and he was so happy about the class because now he's using all this stuff at his new employer, and he's impressing people with his skills. Right? So it goes a little bit both ways. Don't take it too hard. Okay. That said, let's start with the homework 3 solution. I'm not going to do homework solutions for every homework. At least I usually implement the solution. I didn't for the last one, and maybe that was a little unfair to Tim. So that's sort of why we got a bad template there, and the homework was also ready like 2 days before the publishing deadline. So Tim had to make a solution. It was a little crazy. So it's not Tim's fault. It's my fault that we kind of screwed up on that one. But either way, in general, I'm not going to talk about homework solutions in every class, but this one seemed pretty tricky, so maybe we'll take a quick look at my solution and see how that goes. And I'll also, of course, publish the solution on the website. Let me make sure this is the right one. Yeah. Okay, so homework 3. I'm sure most of you tried at least. So the basic idea is we're starting by grabbing the range of global addresses, global variables, and the range of addresses that hold the stack. Now we go through every pointer worth of those ranges. So every 8 bytes, we pretend that may be a pointer, right? And then we check, is it a pointer, by calling a function that we write that sees it, does it fall within an allocated malloc chunk? If it falls within an allocated malloc chunk, then we say it's a pointer. Okay, so the first step, actually we'll go from the bottom. When we call GC, what do? We figure out where does the heap end, where does the stack start. Yeah, okay, so it's upside down for some, yeah. Anyway, and then we build an index. We can ignore that for now. It works well without the index. And then we run through the global variables, just to look for those pointers, and then we run through the stack variables, look for pointers. And anytime we find a pointer, we mark the chunk that it points to as, okay, I've seen this. And then we go through that chunk. Okay, so you got to do this recursive thing, right? You have a pointer, global pointer to one chunk. You have to run through that chunk and look for more pointers because we want to explore the whole graph. Okay, so but you don't revisit the chunk that you've already marked, because otherwise you'd have an infinite loop. Okay, so once we've marked everything, there may be some chunks out there that are not freed, but they're still not, but they're also not marked. Those are garbage that needs to be collected, and we find those by sweeping. The sweeping part goes from the beginning of the heap, just adds the size of each chunk over and over, iterates through all of the chunks, and looks for a chunk that is in use. So the bits. So it's the bit after, the lowest order bit in the chunk size right after is set. So it looks for a chunk that's in use, and that's also not marked. Right? If it's in use but not marked, it's garbage. So then we just call free on it. So we'll see there's one very tricky aspect about that one too. Okay, so walk region. Pretty straightforward. Iterate through every 8 bytes. Why does this cause it to jump 8 bytes? Anyone? It says I see. Very good. Okay. Before this class, you'd never have gotten that one. I think. Maybe someone. Okay. So then here's a tricky one. We got to make sure that. So this is because of this index optimization. Right? I have a little index that has pointers to chunks. It's a global. It's an array that's a global. So if I'm looking at one of those, that doesn't really count as a pointer to a chunk. It's just an optimization internally from my garbage collector. If I have that pointer, that doesn't mean that what it's pointing to is not garbage. So we need to ignore those. But if it's not one of those, then we want to see, is it a pointer? If it's a pointer and it's not marked already, the chunk isn't marked already that it's pointing to, then we mark the chunk and then we walk that chunk, looking for more pointers. Okay, looking forward looking a little further up, see if something's a pointer. Well, it's got to be first inside of the heap. Okay, so we only count those. We're only looking to garbage collect the heap here. So, yep.
Yours would probably infinite loop if there was a pointer on the heap itself, because it doesn't first check if it's already marked or not.
Let's see. Over here?
Yeah, before it marks it, it doesn't.
Here.
Oh, okay. Okay.
Okay.
Never mind.
Okay, so of course it has to be inside the heap, and then we're using this heap index, and we'll ignore that for now. Right? So this is just a way to speed things up. Let's pretend here that the chunk is just the first chunk on the heap. So now I'm running through chunks on the heap until I find a chunk that's, let's see. Oh, it doesn't quite work. I mean, the solution works, but I think we have to deal with the heap index at the same time. Oh no, this works fine. So now we're starting with the very first chunk, let's say. We're running through the heap until we find a chunk such that it ends after our pointer. Right? So all the previous chunks, they're ending up before the pointer. The pointer's over here somewhere. Now we're iterating through, and eventually we find a chunk that overlaps with the pointer. Okay, so now we have the right chunk. And then if that chunk is in use, we return it, otherwise we return none, because if it's a free chunk, that doesn't count as a pointer either. Anyway, yeah.
The heap index, is that just like something, is that just you went through the heap and built it with all the chunks?
Yeah, so we'll talk about the heap index just after the basic solution. That's only there to speed things up. It doesn't affect functionality at all. You can replace this here with just bottom, and it runs the exact same, only much slower. Another question?
Never mind.
Okay. All right, so that's is pointer. What does that leave us with? Well, we have to have a sweep. So of course I'm ignoring these little functions, like the mark function and so on. We can maybe look at those too, but they're not so important. So here, the sweep part, running through, we're starting at the very top. I didn't actually have a bottom pointer, so this is, I'm using the template, right? So there's heap mem start, and that's actually, for some reason, a malloc pointer. Right? So you gotta subtract 1 or 8 bytes to get to the beginning of that chunk. Okay, so now we're running through all the chunks again, and here's the tricky bit. I wrote this down in the comments. So in general, with your code, we're not usually doing code review, although I think Tim might do 1 or 2 with those people who are interested later in the semester. But as a general sort of idea of how to use comments and how to write good code, you really want to put comments when there's something tricky going on here. Like when your code is like, what's happening here? Right? Then you want to put a comment. You don't. I had a student who for years was putting comments like this. Assign chunk to, and then whatever is after. Right? Okay, so there was a comment for every line in the whole code. And you absolutely don't want to do that, and in part because it makes things difficult to read, but also in part because when you then change your code, it's very likely that you didn't change the comment. Right? So, well, now what's going on? Whereas when you do things like this, you need some clarification, so you can at least try to figure it out after. So be spare. No, you don't want to have too many comments, but try to use them wisely when you can. Okay. So here the tricky bit is this chunk stuff. It's kind of like a linked list if you want. Right? There's a size before, and you jump forward to the next chunk, and there's another size. So now I'm at a chunk, and I free it. What's malloc gonna do when I call free? It might coalesce that chunk with whatever's before and whatever's after. Right? So now suddenly my size might be gone. Right? If I try to use the size after I call free, it might have changed. If the one after got coalesced. If the one before got coalesced, I don't know what happened with this size. Maybe it's still there. It's probably not going to be very useful. And of course, the chunk after, if that was free and I got coalesced with the chunk after, that chunk doesn't exist anymore. Right? It just disappeared. So now I have to, well, I can't go to just add my size and go to the next chunk because that wouldn't mean anything. So, okay, so here's the tricky bit then. First we have to see, whatever's before doesn't matter. Because we're, at least if we remember our current size or something, that part is easy. But if the next chunk is free, then that's going to get coalesced. Right? So we have to check that first. So here, first I'm getting my next chunk. Clear that. Okay, so here, now if the next one is free, then we have a tricky thing, right? Then we actually want to just ignore that, because that's going to get coalesced, jump onto the next one. So that's what we're doing here. I can imagine many of you tripped on this one, because that's a hairy little thing. Okay, so then we're freeing it. And now I can free it, that's fine. But I actually had to save the next pointer before, because I couldn't compute next chunk after freeing, because now it's the value in there is undefined. It might still be there. Most of the time it probably will. I don't see why malloc should rewrite those bytes in memory. But it might also decide to put the free pointers in there. The free list pointers, they might end up on there. Depends on the size of the chunk. So anyway. So now, yeah, so if you find a chunk that's in use and it's not marked, we gotta free it. We do a little bit of trickery there to make sure we do it right, and then skip it. If it's not in use, or if it's not marked, then we just, okay, so this and is not marked, I don't know. So this probably clear mark wouldn't have to run all the time, but I do it anyway. Just make sure, we don't want to leave any marks around, because next time, malloc could get confused by all these marks. That's not good.
Free anything that's like the mmapped. It'll refuse.
Yeah.
It thinks it's mmapped, aka LSB2.
Right. So malloc will for sure free things that are mmapped, but probably not if they're also inside the heap.
Right.
Right. It's got to be one or the other. But we're using the mmap bit. If we're using bit number 2, and I think I'm using bit number 2, but I don't remember. Yeah.
What's the functional difference between a void pointer and a size t pointer? Do they seem
There is no difference really.
you can't reference a void pointer, but you can a size t pointer.
Right. That's the main difference. Right. So a void pointer doesn't really it doesn't really point at anything. Right. Whereas a size t pointer, you know that you reference it, you get a number.
So what is the mode that we're using a void pointer versus size t pointer? Is it
Because that way, if you do plus size, it will do mapping on the list.
Both of them are fine. Oh, let's see. A void pointer. Yeah. If you add 1 to a void pointer, it actually adds 1. If you add 1 to a size t pointer, you get size of size t added.
Okay, so the void pointer can manipulate the address itself.
Yeah. Same as with a car pointer. Actually, a void pointer and a car pointer, they're very similar. Size t pointer acts a little different because of that addition bit. Yeah.
When something gets free, other than the little bits that does with the size is, it doesn't actually change the data, right? That is currently there.
Well, that's not quite true, because remember the free list.
Right. I remember
So there's some
free-
pointers. They're stuck in the same data.
Right.
So part of your chunk is going to get overwritten by these pointers in the free list. But most of the data will be safe. That doesn't mean you should try to use it.
No, I realized that I made this mistake. It didn't have to change anything about my program, or it still ran fine, but clearly this is something I should have taken care of.
So probably your chunk was large enough that it didn't matter, or something like that.
That explains why it would crash if I had very few chunks.
Ah, yeah. Okay, so that's the sweeping. So that's all the major functional code, I think. Oh no, oh yeah, so then there's the heap index. So the way my heap index works, I have to draw this. Let's see. So we'll, no, that's not it. There. Okay, so I have my chunks, right, of various sizes. I'm just gonna, okay, I'm not gonna draw lots of different sizes, so we'll go like this. Okay, here's my heap. And then I have a heap index, which is a bunch of pointers. So I don't know if did Tim discuss the heap index in lab? Yeah, I think he made it a little more complicated than it needed to be honest. Okay, so let's make a short heap index. Mine has 1,000 entries, but it'll probably work okay with 100 entries too. The basic idea of the heap index is to make sure you don't have to run through the whole thing all the time. So we want to be able to quickly find something that's nearby using the heap index. So my pointers, these are all pointers. They point at some chunk in the heap. And they're all going to be, they're valid chunks, but they're not necessarily in use. That doesn't matter. They're in use or they're free, I don't care. So when I build the heap index, I run through the entire heap, and then I assign pointers such that it points every, okay, so say this is now 1024 long. I have 4 of them. That means 256 byte intervals for each of them. So now every 256 bytes, roughly, there should be a pointer to some new entry. Okay. So they're approximately uniformly spaced. Actually, it probably is going to end up more like this. Yeah, okay, more or less. All right. So now to find the corresponding object for a pointer that's pointing at the heap. So say I'm pointing now here. Not at the beginning of it. I'm pointing anywhere in it. I first look at the value of this pointer. I see, okay, which of these ranges does it fall within? Right. So that's a question of dividing. Right. I take this pointer minus the top of the heap, or the bottom of the heap, that is. Sorry, yeah. Zeros are over here now, the way I'm thinking, instead of over here. So I figure out which range. Okay, now I have the range, but that's only going to get me to the top of this chunk. So now I iterate through the chunk until I find the actual chunk that I'm interested in. So I could start with any one of these before. I could start with this one. That's what we do by default, right? Iterate through. But if I, it's handy to have these shortcuts. So I take whatever shortcut that's guaranteed to be before my the pointer I'm interested in, and from there I iterate. Then we're good. Okay, so if I do my math wrong, I might get this one, and then of course it's going to crash, right? Because I iterate and it doesn't find what I'm looking for.
In your code, what's the memset function you're using?
I don't think this is necessary. I was being paranoid. Oh, I wasn't paranoid. No, I was running GDB, and I wanted to make sure that I got valid entries inserted into my index. So I just memset the whole thing first to zeros, so that as it's running, I see it filling up.
Oh, so it's a calloc.
What's that? It's
Calloc.
Oh yeah, you could use. Well, you can't use calloc because the index is sitting in as a global variable. Calloc is malloc, but it nulls everything. Memset just sets everything to whatever you specify. So I said here, set them to zeros. It's the same as for looping. For every entry, set it to 0. Okay, so that was just to make, this is not necessary, it's just to make it a little easier for me to debug. Like looking at the values, it's easier to tell that a 0 is not in the heap than some random value that's not in the heap.
So heap index is the start of the array?
Heap index is the array.
Oh, the entire array?
Here. Yeah. But if you just use the name, you always get the start of the array as well. If you say dereference heap index, you get the first element in the array.
But how come, so with that, does it zero out the entire array? Or
Yeah.
just the first? So
Yeah.
how does it know how big it is?
That maybe. Size of heap index might have something to do with it. Yeah, so now how does C know how large the heap index is? That's a good question. If heap index here was a pointer, then I would get 8, right? But it's not. It actually has an array type, and those can only be statically declared. You can't dynamically make arrays, things like that. But yes, C is a little clever when it comes to arrays. So
If it was double star, it wouldn't work.
no, then you get 8 because the size of a pointer is 8. Okay, so here we're just blowing through this. I think we'll skip the arithmetic probably, but I'm running through every chunk to see, oh, is this the one that should go in the next slot in my index? And if it is, okay, then I assign it and increment I, and I'm set. Okay. Was there anything more? Let's see. Yeah, so these are fairly obvious, I think. Next chunk. There's another code review or trick for how to write good code. Make sure that your functions and your function names, and your variable names, where it matters, have intelligible names. Even if it means typing a little more, you know, next chunk is going to be infinitely better than NC, right? Or even next. Right? So here I'm passing in a C here. Yeah, I don't know. That's probably fine because it's such a small function. I can probably live with that. Chunk might have been nice too. Or current chunk. Okay, here's one. I don't know if, I don't remember if the template had a lot of these defines in it. A function is, that means in the assembly it's going to be a call, right? It'll be saving the stack and saving the stack pointer and things, and then you have a return and so on. So there's some work involved in calling a function. A define is not like that because this only exists before the preprocessor comes into play. Right? So once you blow through the preprocessor stage, this define here doesn't exist anymore. Instead, this every place where it says chunk size C, like this one, gets replaced by this. All right? So don't use those. Don't use defines. They're extremely difficult to understand and debug, and it's just a mess. All right? So when you write your programs, do them like this. Clear mark. See, these are stupid little functions. A lot of extra overhead to do this. It could have been done with a define. Don't. All right. So I actually started out with Tim's solution. And he had lots of defines because he's a kernel hacker and he wants everything to be really fast. Right? And it's very important when you're all the way down there to make it fast and so on. But start out by writing functions and then run gprof. Right? Profile your program like we did in the previous homework. See where are you spending all your time, because one of these functions might be really hot. You might be making millions of calls to this function. Find that one function. In my case, it was chunk size. It was 85%, I think, of my execution time was spent in chunk size. So I decided to make a little hackery there, right? Replace that with a define. Now everything gets inlined. There's no function calls. Goes faster. The whole time doesn't disappear, right? Because there's some computation here, but this is probably a small part of the total execution time.
Instead of define, could you also just make an inline function?
Yes, an inline function would work. In this case, I don't think you get to put an inline function here. Maybe if you have it in your header file, it might work.
Define this extern inline.
Extern inline.
A hackery I found on some website.
So I should look that up. I'm not familiar with.
How important is it to define the number 3 as size t? I assume it's important.
Let's see the number. Oh, this. Oh, so what this does is it just a different way of writing 0x FFFF.
Well,
How many FFFF?
It's
Oh.
just the actual size t of 3 rather than just
Yeah.
3.
So what I was worried about was that this 3 there might not be represented as a 8-byte. It might be a 4-byte.
Yeah.
All right. So then I only get how many? 7 of these. Like that. And I wanted a bunch more of the Fs. So I'd made sure that it's the right size first. And this is real hackery. Just you can just write out the mask as well. It's fine.
Feels good to write it that way, though. You can just twiddle the 3.
It looks nice. Yeah.
You can just twiddle the 3 and
Okay. So that's chunk size. Here we have the other marking things. Very trivial. This was part of the template, and that's all there is. Any more questions on this? You were looking at something?
No, see, it's not a subtraction, it's a not.
Is it in
Oh, it is. Okay.
Yeah, this is a not.
Tilde.
This is a-
That's what it's a subtraction. Wait, what?
This is a binary not, or bitwise not.
Yeah, no, I blew by a subtraction sign.
Ah, yeah, that wouldn't work.
I don't think so.
Okay, so I'll make this code available, and in general, we make all the code available. It's a good idea to try to read through it. Maybe you'll catch a trick or two in there. Right. Okay, so that brings us to homework 4, and I know Tim gave an introduction mostly to the tools. So typically we'll do the introduction to the whole homework in the labs. This time there's a lot of tool use, and the homework is quite different. So we'll spend a little bit of time on that here as well. And besides, that homework was only, I don't know, did anyone notice? You probably didn't. When did the stuff get added to your SVN? We'll see if we can figure that out here.
They actually
The template. Yeah, so let's try this. SVN log. Oh. Does anyone want to volunteer their H4D2?
Two.
Homework 4. What's wrong?
I don't remember which one's which, but
Unknown host name, bits. Oh, I don't have an internet connection.
thanks, UIC.
Yeah, very nice. I am associated with UIC Wi-Fi, but of course there's no internet connection. Okay. Anyway, I'll just let you know that was added at 3 a.m. So I'm not you're not the only ones working late on homeworks. Okay, so let's go to the homework page. Oh, right. Awesome. All right, I do have one of the many dongles you need with an Apple computer to get connected. Oh, there.
Is that a USB Ethernet?
USB to Thunderbolt. Oh, sorry, yes, of course. Ethernet to Thunderbolt, yes. I'm sure they will change the standard next time. Okay. Yes, there we are. Good old Ethernet. When you take CS450, you'll get all of the details on how that all works too. It's a networking course. Okay, so did you all take a look at this? Probably, right? So the whole thing here is we don't have any source code. Be very sure that you run the program like this. So this is turning off, this part here, is turning off that address space randomization. The template itself doesn't work with address space randomization. So that's actually also the case for lots of these copy protection techniques that they used to use in older software. That they also stopped working when they turned on the address space randomization. Okay, so in that sense, it's realistic. So there's a bunch of like pointers being assigned or values being assigned that depend on the address space layout that are happening in the template.
But wouldn't be able to work on an offset?
I think there is a way to write the template so that it works with address space randomization. Yes, it isn't written that way, and probably your life would be a lot harder too. Okay, so there really is not much to this homework in the sense that it'll be the fewest bytes edited so far. But what is tricky is finding out what's going on. Oh, I need my Amazon machine up. Huh. Has anyone figured out how to change the password?
I don't know how to do so. I've tried.
Okay. Right. Okay, so while we wait for that to start, there's a few little steps to it. All right. First, it's verifying the key locally. then it does something. So if it's not a valid key, then it just says, okay, no, go away. If it is a valid key, it does some other trickery. And then it starts asking the server to validate. So there's a server that the server doesn't actually validate the key. It just records the fact that you're activating the application. Okay, and then once you send something to the server, whatever you send to the server, really, it'll respond with a little bit of more binary. And that binary, that code is actually necessary to run the program. So the program cannot run in the current form, even if you have the right license key, without contacting the server.
Does the binary key change depending on if you have a valid password?
No, whatever comes back, it always sends back the right stuff. It's not a key, it's actually code. It's part of the program. So it sticks that inside one of its old functions. Right? There's some function in there that has just junk in it. It replaces that with whatever it got from the server, and it calls the function. And that function then calls other stuff, and the whole program starts running. Okay, so that's sort of how the program works. It's a silly little program, but okay. I think we're probably up and running here. Let me get. So, hello. I thought we'll run the template, and we'll also run the solution and see how they differ. Okay. Okay, so if I just run make, there's, oh, right. You of course don't have the source code. So this isn't a, so there's all this source code here, lib.c and homework4.c and stuff. I just ran make here to make a clean template. For you, you just get the two binaries. So what you're going to get is the lib.so and the, where is it? Yeah, the homework4. So let's try running it. As always, I got to get the libraries right. And we have to run it with the address space randomization turned off. Okay, please enter your license key. Key. Okay, that's not the key. Okay, maybe I'll be nice. Okay, so I'll provide you with one license key. There is one that exists and that actually works. So just to see how things work out, we'll type in the actual key. 361, 2431. That's the only one that works. And you're not supposed, you're not going to use that when we evaluate your program. But it might be fun to see what it does. Okay, so now it actually talked to the server, and then it's running this fantastic program. Okay. And there it is. Okay, so this cool little program, you actually want to crack this so you don't have to get a license. And now we have to make some changes. Okay, so let's try my hacked version. So in order to do that, I have here homework4.hex is one that I prepared. All right. Now you can, if you want, you could read through the video here and try to find which bits were different, and hopefully maybe you can get it to work. Right? Probably not. Yeah, probably not worth the time. And in fact, it may not even have shown the relevant bytes because I didn't go through the whole thing. Okay, so in order to make a hex file like that, I say xxd homework4. Now it just outputs it on the command line. Right, so there, that's the contents. If I want to put it in my hex file, I go like that. Right, and then I can edit it. But now I've actually prepared this already. So now I go xxd -r homework4.hex. So that returns it from the hexadecimal format into binary again. So now I have a homework4 with the, I should run it with the this with some hacks to it. So now I put another key. Oh, that actually worked. Okay, so that's nice. Everything seems to be in order. But the problem is it contacted the server, right? So if we go to that server page, hopefully that still works. So here we are. I got caught. So this is the proper license that was used, but now I use some other key, and it actually knows where I'm running this from. Right. So this is the.
You're going to jail. It'll lock you up.
Yeah. So that's the problem. Right. So maybe if this happens a few times, it's not a big deal. But if it keeps happening all the time, you know, someone's going to be wondering what this pirate is doing here and why are they not in jail, right? So we got to make sure that it doesn't contact the server, and to do that, we have to also edit the lib.so. So there's some stuff happening in homework 4, and there's some happening in lib.so. So we got to edit that one. And so I have the same thing prepared. Lib.hex, I think. Yeah. Let's try it one more time. Okay, so it doesn't talk to the server, looks like. But we can double check over here too. Yeah, so nothing new on the page. Okay. The programs are the same size. In fact, if you try to change the binary size, you're probably going to just run into trouble. And so we're going to evaluate your program using CMP, which takes 2 binaries as input and says, oh, these bytes changed. Okay, so that's part of it. We're going to make sure you didn't change too many bytes. Like, we don't want thousands of bytes changed there, because that means you used some tools and some, you know, maybe you compile a new program that does the same output. Or, you know. So that's not the idea. And then you're also expected to write a little file that says patches applied. That's the name of the file. And so you just have to explain sort of very briefly what changes you made and why. So you say, okay, I changed this pointer to point to over there because then it does this. Right? Okay, so let's see. How are we doing on time? We have a little bit of time. Sorry, question?
We edit the lib.so the same way we edit like the form. We want to go through the same process and figure out where it connects the server. Or that like
Yes, of course. Yes. So same thing. You do a xxd lib.so, and that gives you another binary. But you can't really, you can't read this stuff. That's completely impossible. In fact, it's very hard. I found it really hard to even find which bytes to edit, even if I knew, like, I want to make this change. Now, where is this byte? Even that's hard. So I don't know how much Tim did in the lab, but let's just see if we can do something about the tool use. And so the first step you want to take, probably, is to do a readelf -a to figure out what's really in these things. And I've been very nice. I compiled all this with debug symbols on, so you'll see all the nice names of everything. And I also use nice names to make it a little easier.
Real server key.
Yeah, okay, yeah, so you recognize this. Yeah, good. So there's a lot of stuff in here. Here we go. Verify license key. Oh, that seems like an important one, right? And then probably we have the main, of course, server license validation. That's a global variable. Okay, not sure what that is. And so maybe that's undefined. Maybe that comes from somewhere else. Okay. Oh, sorry, it's a global function. Okay, so maybe that's something that comes from that shared library, right? It's undefined in here. Okay, but we have some functions. Maybe we'll see what functions are actually in here. Was it func? Yeah. Okay, so most of this looks like it's just stuff from libc. Probably not so important. That one does look fairly important. And then, what else do we have? Same one again. It's funny. Oh yeah, so I don't know why there's 2 of them. Okay, So that's a start. But let's see with object dump then. See what's really going on in here. So if we go to main, that's where it all starts. Fortunately, this is a short program, right? So you can actually read the whole thing in assembly. It won't hurt you. Okay, so what's happening here? Okay, something with a net ID. Okay, so that's probably like it's custom for everyone, right? So maybe that's got something to do with this. It actually prints out on here. It says who, so that's my net ID. All right, so that's where that came from.
You can technically change that to say Jacob.
Right, but you still get in trouble because the IP address. Yeah. So it doesn't matter what you send.
Technically fake that too.
No, technically you can't fake that actually. That is so if you were sending so that's a CS450 topic, but with TCP you can't fake it. Of course, if you were to use one of those anonymization servers, yeah. So that's not a question of changing the program, but you can use someone else's computer to send it, and of course they're going to get the blame. Yes.
And you can safely read the binary you're supposed to send to George.
Right. And there won't be any trouble at all here by you running this as many times as you want while you're testing. No one's calling the cops, right? So you can read the binary at your leisure. But then when we test it later on, we don't want to see any messages showing up on the server. Okay, so here we have some other, I don't know what's going on here, but that looks relevant. Okay, so here we're calling, we're getting, oh, here's an fgets. So that sounds like we're probably reading in the license key, right? And here we got a call, well, it's not a call, it's actually a jump to verify license key. Oh, this is the wrong one. I'm going to have to redact that because that was the solution. So,
We saw nothing.
well, actually, that's a perfectly fine way to do things. You can put a jump you think is relevant. But it's not the only way. And I was thinking after I did the solution, I was thinking, maybe I could have done it this other way. That was easier. Right, so don't take it too seriously that there was a jump there. Anyway. So here we're calling this verify license key. This seems very reasonable. We're typing in some text, and then we're calling verify license key. Okay, so that's probably where the action is, right? So let's see if we can just find this call in the binary. We want to change that call, make it call something else. What are we going to call instead? We have nothing else. We can call main instead, maybe. Right? Call back to main. That'll be frustrating. Let's try that. Okay. So here we're calling. Okay. So what's going on? That's the binary. Right? How much time do we have? Okay. This is the binary code. That's the address we're calling. What's up with that? That doesn't look the same at all.
It's in the retail. It's a undefined.
No. Verify license key is part of this. If we just roll up a little bit, it's in there. There it is. Verify license key.
It's an offset.
Right. So this is not. That's an absolute address, but this is just in the nice disassembled version. In the actual code, it says call. That's the E8 or call Q. That's like a 64-bit call. Relative with this number. That's a negative number. Of course, it's Intel syntax, so you got the least significant bit here. So it's most significant there in that order. Okay, so it's call minus FF, whatever the negative number works out to be. All right. So it's not a huge number because it's if you take FFFFFF minus this, that's the difference, right? That's how much negative it is. The way it works, -1 is all FFFs, right? FFFE is -2. Okay, so this is going to be minus what? A few hundred, something like that. Yeah. Okay, so now we need to figure out then, if we're going to change this call, actually we don't have enough time to change the call, but we'll find it at least. So if we want to change it, then we have to figure out first, what's the offset between here, all right? This address and that address. Figure out that negative, all right, in hex. put those 4 bytes in here. And I promise you, those 2 are going to be FF. That one probably FF as well. This is going to be a something like, what is it, 40 or so. Okay, so let's just find it.
That's the direction it goes. Was that the whole big endian, small endian thing, or was that something else?
Yeah, that's the little endian, yeah, Intel. Homework 4. So, what was it we were looking for? Find it again, sorry. We'll be there very shortly. Okay, here, E89AFE. Okay, so that's probably a good place to start looking. E89A. Oh, there's no E89A. What happened? Well, all this is in the 4-byte chunk, or 4 nibble chunks. So maybe it was just an alignment problem. We'll try E8 space 9A. Ah, there it is. E8, 9A, FE, FFFF. That looks familiar. That's probably it. Now you want to double check a few bytes before and after in that object dump as well to make sure it's the right one, because maybe you're changing the wrong place. And then we stick in the right values. FF, perhaps. Save that. Actually, let's just do it. See what happens.
You don't know if that's the right value, right?
No, that was some bullshit value. It's probably going to crash. Ah, Schmod plus X, homework 4 test. Ah, where am I run? Thing, there. Yeah, so that you're going to run into that one a few times, I'm sure. Okay, hello. Oh. Dun, 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 dun.
Surprise, surprise.
Okay, so there it is. See you on Friday.